No discussion of special relativity would be complete without talking about the twin paradox. The story goes something like this. Alice and Bob are twins, and on their 20th birthdays, Alice gets on a spacecraft that's going to take her off to a distant star. The star is 8 light years away. It's the Seaford system, and Alice's plan is to travel on her spacecraft at 4/5 the speed of light until she gets to that star, takes some quick measurements as her ship turns around quickly, and then she's going to come back to Earth at that same original 4/5 c, 4/5 the speed of light. Meanwhile, Bob stays home the whole time, minding the store or whatever Bob does. And the question in the twin paradox is typically, how old is each twin when they're reunited? How much time has passed for each one separately? And so we can analyze this in a relatively straightforward way. First of all, from Bob's perspective, Bob says that Alice's speed is 4/5 the speed of light, or 4/5 light years per year. And that's, of course, equal to, not delta t on top, that's equal to the distance divided by the time. That's the definition of speed, and since Alice is going essentially constant speed on her way to the Seaford system, we know that that is her 8 light years divided by delta t, and just by ratios or simple algebra, you can immediately figure out that delta t is going to be 10 years. So Bob, watching Alice's travels, will believe that it takes Alice 10 years to get to the Seaford system, 8 light years away, and 10 years to get back. So Bob expects to be, Bob sees total time there and back, 20 years. He's 40 years old. He's celebrating his 40th birthday when Alice gets back home. That's Bob's story. Now we turn to Alice's story. And to understand Alice's story, we know in relativity that a moving observer, that if you watch someone who is moving relative to you, that you will see their clock ticking slowly. So we expect that Bob is going to see Alice's clock ticking slowly as she goes. And to do that, we could use some equations, or the thing I like here is using space-time diagrams to visualize all of this. We can use a space-time diagram with position horizontally and time vertically to visualize what Alice's experience of time will be. And in particular, I'm drawing this on this hyperbola graph paper, which I got from Professor Tom Moore of Pomona College. And on this hyperbola paper, the hyperbolas can be used to calibrate our understanding of a moving observer's experience of time. So I'm not going to go over the theory behind it, because I think we've learned that already. But let me talk about how you can actually use this to figure out Alice's experience as she goes. So, as usual, we have to draw Alice's path in here. Bob's path, of course, is straight on Earth. He's sitting still, and remember, sitting still means going vertically on a space-time diagram, because you're not moving in x at all, only in time. Alice, however, is moving, and she's moving at 4/5 the speed of light. So she starts at Earth, and every time she travels 4 light years, it takes her 5 years to get there. Again, 4 more light years, 5 more years. So let's see if this pen does what I need it to. Just a second. Let me try to get Alice's experience on here. All right, it's always important when you're using space-time diagrams for this sort of thing, always important to make sure you draw your lines very carefully if you're not using equations to double-check everything, because the more carefully you draw your lines, the more precise it's going to be. And so this is Alice's path from Earth to the Seaford system, and if I want to use that to calibrate, use the hyperbolas to calibrate Alice's experience of time, what I do, I look at every point where Alice's path intersects one of the hyperbolas, as usual. So here is 1 hyperbola, here is 2 hyperbolas, here comes 3 hyperbolas, here's 4 hyperbolas, hyperbola number 5, and hyperbola 6 is right there. This is telling me that Alice's perception of time goes along, and for her, she only experiences 6 years of time in the time that it takes her to get to the Seaford system, moving at 4/5 the speed of light. So where Bob said that it took 10 years, Alice, maybe I should label this as Alice's path. Alice's path, Alice measures 6 years to get out there. Then, of course, we said Alice very quickly turns around and comes back. And for that, turning around and coming back, we can go back here. We're going, of course, she can't just like bounce off instantly. She's got to slow down and speed back up again, or at least go around the star or something to change direction. We're going to assume that happens very quickly. We can take that simplifying assumption. It actually doesn't hurt much to assume it's very quick. And so she's going to turn around and come back, and I know where this is going now. I know it's going up to the 20-year mark, because we already did that calculation. We could also do it by counting things and stuff, but here we go. Let's go. Okay, whoops, Alice overshot. Well, okay, that's Alice's experience going back. That's her path going back. Now, this is a crucial part of twin paradox measurements on hyperbola paper. We cannot pay any attention to the hyperbolas on the way back. Why? Because the hyperbola calibration method, using this paper, only works for lines, for paths that go straight through the origin. Any line that does not pass through the origin cannot, must not use the hyperbolas for calibration. So, in particular, there's a temptation to start counting all these hyperbolas. No, don't do it. What you want to do, you have to calibrate this in some other way. Now, there are several ways of doing that. The idea of it is we know that Alice is moving at the same 4/5 the speed of light that she was before in this particular problem. And so because she's moving at 4/5 the speed of light, we know that the rate at which her clock is ticking, as measured by Bob, for example, has to be the same on the way back as it was on the way out. Otherwise, that wouldn't obey the way that relativity works. To really justify that, there are a few things we could do. One thing would be, if we had a larger sheet of hyperbola paper, we could just take this path, measure its direction and its length, copy it down from the origin going up that way, calibrate it there, and then copy the calibration back to the real path. That's one option. Another option would be to, and this one, one of my a group of students last week came up with this. Another option would be, well, we know Alice is still moving the same speed in this particular problem. She's just changed directions. So here's what I'm going to do. To get the calibration right, most of the way at least, I'm going to pretend Alice's path continues as it did before. Oops, come on, path. I'm going to pretend, I said, that it continues as it did before. And I'm going to say, if she's moving the same speed, I can use this. I can use the hyperbola to say what her experience of time would have been if she kept going straight, and then just translate that horizontally over to what her experience will be in this case. So if I do that, this would have been her fake 7-year, her fake 8-year, her fake 9-year, 10, 11, and I guess 12 would be right up here. So let me carry those calibrations over to where they go on this side. So that is 7, get the horizontal right, 7, 8, carry this over, 9, 10, 11, and 12, right back to Earth when she gets back. Another way of doing it would be to carry these up straight above one another. That's another way, since it's the same speed. Of course, if it were different speeds there and back, you would need to recalibrate using a copy of the thing. But this gives us the idea. If she's going the same speed out and back, we can calibrate that way. Again, notice these calibration marks have absolutely nothing to do with the hyperbolas anymore. The hyperbolas are useless on the way back. The hyperbolas are only useful for lines that go through the origin. Okay, so what's that tell us? That tells us that Alice returns home, and it's been 12 years. So for Alice, she sees 12 years travel. So when she gets home, she's 32 years old, and she looks at her brother Bob and sees that he's getting gray hairs and rounding belly or something, and she laughs because she's still in her early 30s, and then she realizes she's been off in a spaceship for 10 years, or for 12 years, and Bob's done all sorts of cool stuff. So, 50-50. Anyway, point is, this is our story. This is the way the twin paradox works. Now, why is it called a paradox? And why did I put paradox in quotes? Paradox usually means that there's some contradiction, or something that's some apparent contradiction in the system. Here's the deal. Some people, when they are first learning relativity, think that the twin paradox is just the fact that, oh, Bob saw 20 years pass, while Alice saw 12 years pass, and that's a contradiction, ooh. And then someone who knows relativity comes in and says, no, it really works, we can do this. Again, we could do the same thing using the metric equation, find the space-time interval and things. We're not going to worry about that right now. I'll believe these numbers. That's the twin paradox. That's not really what people mean when they mean the twin paradox. That's the like baseline level of the twin paradox. It seems, oh, it's a contradiction, but no, relativity says this. If you know how to use hyperbola paper, you know that this works. Now, a paradox, if someone talks about a paradox, it's not, oh, something in this new theory is unexpected. A paradox is, oh, something in this new theory contradicts itself. It's internally inconsistent. And there is a period early on when people were grappling with Einstein's theory of relativity where a fair number of people, even well-respected physicists, thought that examples like this one meant that the theory of relativity, while elegant in some ways, was self-contradictory and didn't make sense. And here's why. The twin paradox, the actual apparent paradox of it, still not a real paradox, that's why it's in quotes, the apparent paradox of it is this. Bob sees Alice moving close to the speed of light, and so Bob sees Alice's clock ticking slowly, and therefore Bob will expect Alice to come back looking younger than he does. But, the objection says, what about Alice's experience? The whole point of relativity is that each inertial observer believes that their clock is trustworthy. And so in particular, Alice, after her initial little boost of rocket engine or whatever, Alice at the beginning there sees Bob as the one moving away. If I were to draw one of Alice's space-time diagrams, I would draw something like this, where Alice went straight up, and Bob was the one who went away and then came back. And so the naysayers, the people claiming it's a paradox, would say, but shouldn't Alice, in her calculation, say that Bob will come back and be the one who is younger? That shouldn't Alice say, oh, the full time will pass for me, even if you say it's 12 years for her, they would say, but look, Alice would think Bob's clock is ticking slower. Alice is going to think that Bob comes back even younger than 32. It's even less than 12 years that have passed for Bob, and that's a contradiction, because you can't have a theory that disagrees on the results of actual physical questions like how many gray hairs have you had, or how many heartbeats have you had, or how many birthdays have you had. So that's the apparent paradox here. But again, space-time diagrams can help us enormously in understanding this. And here's how. We know on a space-time diagram that not only can we calibrate an observer's personal experience of time, we also have this idea that we can see what events an observer thinks are simultaneous. We can see what set of events work that way. And we've done that with what I've called time slices, or moving observers calibrated x prime axis or something. What we do, we say, what are Alice's time slices? What are the sets of events that she thinks are simultaneous? So in particular, we know that if Alice is moving at 4/5 the speed of light, 4/5 light years per year, and we've tilted down by the appropriate angle from the vertical axis for Alice's path, Alice's time slices are tilted up by the same angle from the horizontal axis. So the slope will be, instead of 4 light years of distance and 5 years of time, the slope of Alice's time slices will be 5 this way and 4 this way, 4/5. So let me draw that on here. And I'm going to do a dashed line, of course, for, let me make sure I get this right, 4/5 here and here. Okay, that'll be a good start. Let me do a dashed line to get this right for my time slice, for Alice's time slice. Where am I? Here we are. This is an example of Alice's time slice that goes through time equals 0. So remind you of what this means. This dashed line shows us the set of events that Alice would calculate are simultaneous. I can't derive why right now. We've done it before. That's Alice's experience of time. Now let me go through. Now, of course, at time equals 0, when she leaves the Earth, she and Bob agree that that's the time equals 0 event at x equals 0. But let's go through and see what Alice's time slices look like at, maybe not every year because that gets pretty dense, but let's do every other year as we go. Remember, the time slices, when we draw them, all have the same slope. So I'm going to go from here. I'm going to go over 1, 2, 3, 4, 5, and 1, 2, 3, 4. And so that'll be something like this. And so for time equals 2, let me get this time slice right. Get this right. Again, drawing this carefully is important to be able to time. So what I'm going to draw the time slice of all events that Alice thinks happened at the same time as her second year of travel, her 22nd birthday. So let me draw this time slice for you. There's Alice's 2-year time slice. It came pretty close to being parallel, I guess, so that's good. Passed through her 2-year point. Let me draw Alice's 4-year time slice as well, and we'll see. I'll also draw a time slice right before 6. Oh, I should count this over, shouldn't I? 1, 2, 3, 4, 5. 1, 2, 3, 4. Try to get the same point. It's going to be right there. Okay. Got this. Got that. Looks parallel. Let's try it. Okay, that's trying to be parallel to the others at least. And I'm going to do another time slice of Alice's just before she gets to her 6-year mark, just before she gets to the Seaford system, just so I can get one more time slice in there. Let me do that 6 years here. Oh, hey, 1, 2, 3, 4, 2, 5. Here's a good line. Okay, got that. Got that. Measuring this as best I can. Best I can. Did I count that right? Just to check. Yeah, okay. Yep, 6, yeah. Well, okay, so trust it. Believe yourself. All right, so I've got this. And again, time slice coming along through here. All those time slices are parallel to one another, parallel lines. And let's look at them for a second. These are Alice's time slices every 2 years, going along, showing her perception of time. And so you can see the time equals 0, 1 goes through Alice's at time equals 0. The time equals 2 time slice goes through Alice at time equals 2 years. Time equals 4 time slice at 4. And time equals 6 time slice at 6. The thing to learn from this is that Alice's experience of time is at an angle, in this diagram form, compared to Bob's. So where Alice thinks that 6 years have passed for her, she looks back at Bob and says, the moment for Bob that is simultaneous with her 6 years, just less than 6 years, I follow it back, is a little less than 4 years for Bob. Let's look at it the other way. If Bob said 6 years, what time for Alice was simultaneous with 6 years for Bob, Bob's time slice is the horizontal things in this graph, it's Bob's graph, so I followed across, a little less than 4 years for Alice. There is, what we've just seen, is that simultaneity in relativity, or that symmetry, rather, of relativity, that each one of them thinks the other one's clock is running slow because of these tilted lines. Each one of them thinks that the other one's experience of time is slower than their own. Thus far, it seems like the paradox claimers are right. It seems like there's a contradiction shaping up here because Bob sees Alice aging slower, 6 years for Bob, we're under 4 years for Alice. But Alice sees Bob aging slower. 6 years for Alice, we're under 4 years for Bob. But here's what we haven't done yet. We haven't looked at Alice's time after she turns around. Because remember, once Alice is going the other way, once she's coming back, just as her velocity is tilted down by the appropriate angle from the vertical axis to the left, her time slices are tilted up from the left by that same angle. That's how this works. And so when I draw Alice's time slices up here, I have to go with that. I have to go with that angle, that the same angle up, but it's going to be different time slices because instead of being tilted this way, they're going to be tilted this way. Let's just do that just to be careful, just to measure through this. Well, I'm going to start from this point. This last time slice here was like a week before the 6-year mark, before she turned around at the Seaford Star. And I'm going to draw my first one going up here a week after she turns around. So it's still going to be basically going through the 6-year mark, but now it's going to be with the other velocity when she's turned around. Let me do that. So if I do that, I've got 1, 2, 3, 4, 5, 1, 2, 3, 4. Let me draw a time slice through those points, get the slope right. And again, you'll see this is tilted down by the same amount that I would have expected that the other one was tilted up. Yeah, you know what I mean. This is tilted right to make this happen. And I guess this goes this way as well. You'll see things get really messy to the right, but kind of but a little bit more sensible on the left. So there's my 6-year time slice on the way back, right after she's turned around. That's her time slice on the way back. 8 years, I can do the same thing. Let me count out. Okay, 1, 2, 3, 4, 5. 1, 2, 3, 4. Get this about right. Something like that. So this is the 8-year one. Again, I'm doing every other one just to save us some confusion. This is already a bit messy, I understand, but if you play along at home, if you try this out, you'll be able to draw the right pictures. And I guess this goes on this side as well. Okay, so 8 years, I've drawn that parallel line going up that way. That's good. 10 years, let me do it again. Now, what do I do? 1, 2, 3, 4, 5. 1, 2, 3, 4. Really? Okay. I'll draw to here about. Okay, let me draw the 10-year time slice, and then fortunately, the last one's going to be really boring because they're together again. Okay. Okay, there's my 10-year time slice, and I guess I could draw this. Yeah, I could draw this just to get it in there. Since I did the 0, I should do the 20. Okay, so on the way back then, if you look at this, I've drawn time slices that are tilted that way, tilted up into the left instead of up into the right, to reflect Alice's idea of simultaneity on the way back. So remember, when she's traveling on the way back, these are all the times that she thinks are simultaneous with those birthdays. So on her 8th year of travel, this line right here are all the times that all the events that she thinks are simultaneous with her 8th year of travel, her 28th birthday. Her 30th birthday, everything she thinks is simultaneous, that's along here. All right, here's where the key difference comes in, the key idea. What happened in the middle? Because you see there's this giant gap. And, well, it makes sense, right? Alice was traveling along. These were her time slices. She was at constant speed. She gets here. At the moment that she's turning around, we could even say, I drew this one a week before she turned around, and this one a week after. But at the moment that she's in the process of turning, she's going to be going this way, and she's going to go back. There will be some instant where she is not moving compared to Bob back on Earth, if she goes straight back, forward and back, if she's not doing a loop or something. If there's that instant, at that moment, her time slice would actually be horizontal, right? At that moment, Alice's time slice, if she's instantaneously at rest, Alice's time slice would be a perfectly horizontal thing in agreement with Bob's. It would be this line here. Oh, that's so messy on the right, but on the left, it's cleaner. Alice's time slice, as she comes to rest and then turns around and go back, is she's at rest relative to Bob. They have the same perception of time, so it's right there. If I had gone somewhere during her acceleration, you can see I would have gone from, as she goes, her perception of time progresses like this. During that period of acceleration, and then on the way back, it stays up there. But during that acceleration, her time slices changed. Not just her motion, it wasn't just her experience of time that changed, but her notion of what is simultaneous changed. She went from these things being simultaneous to these things being simultaneous in the course of a week. So let's think about what that means. Well, why is that? Why is that? Why did that happen to Alice and not to Bob? The whole reason that Alice's time slices do this crazy whoop thing, that whole reason is that Alice was the one who felt an acceleration. Acceleration, remember, is a change in velocity. And special relativity, we can only do calculations in relativity if the calculations are discussed in a frame of an observer who is an inertial observer, an observer who is not accelerating, changing their velocity. Bob, sitting on Earth, is essentially an inertial observer. I mean, yeah, the planet's going around the sun, it's spinning on its axis, but that compared to traveling 4/5 the speed of light off to the Seyfert system, Bob is basically sitting still. He's essentially an inertial observer. So Bob's experience of time is, this diagram is drawn from Bob's point of view back on Earth, and that means that it matches Bob's inertial observer point of view. Inertial observers are where we can trust special relativity. Alice was an inertial observer for most of her trip, and on most of the trip back, but there's a brief period here in the middle, and I guess at the beginning and the very end. There's a brief period right here in the middle that's the important one, where Alice was emphatically not an inertial observer. She felt an acceleration. She was pressed back into her acceleration couch or something because she was accelerating. She was changing from going very fast away from Earth to very fast toward Earth. And so that's where we have to think of things differently. That's where her experience differed, and where we see her time slices during that acceleration, because it's changing her slope on the diagram from this way to that way. As she accelerates, we see that change in time slices as well. There's actually a lot of interesting stuff you can calculate with this. Some people say you need general relativity to explain Alice's experience, and I suppose that's technically true. General relativity helps a lot for explaining Alice's experience. But it turns out that I've got a video that you can look at that talks about constant acceleration motion in special relativity, and it will talk about how you can use these time slices to visualize Alice's experience. Even though she's an accelerated observer, you can still say at any given moment, what's her idea of simultaneity, and that will make sense for her. In fact, I'll say one word about that now. In general relativity, there's a statement that if you, for example, are in a very strong gravitational field, like if you get close to a black hole or something, that you will find that time passes more slowly for you than for people far away from that black hole. That's just the way gravity affects clocks in general relativity. And general relativity also says that acceleration and gravity are indistinguishable, that you can't tell the difference between accelerating and a gravitational field, a uniform gravitational field. All right, so what's going on here? Here's the idea. Alice feels herself pushed back into her acceleration chair or something when she makes the turn, right? She's feeling that strong acceleration backward. Well, that is, in general relativity terms, comparable to having a giant, black hole or something close behind her. She's got a big black hole right behind her, so she's close to the black hole. She doesn't really, this is just sort of an analogy, but she's close to what feels like a big black hole behind her, and Bob on Earth is far away from that big black hole, much farther away than she is, 8 light years away. And so Alice, then, will expect that her clock will tick slowly while she's close to the big black hole, while Bob's clock will tick much faster since he's farther away. So that's how general relativity, that's a very, very rough way, that general relativity would account for Alice's experience remember Alice's belief here, Alice's experience is, she thinks that she's aged 6 years and Bob is hardly even aged 4, and then over the course of a week or two as she turns around, Bob ages, what is that, 8 years, 8.5, 9 years in that brief time that Alice was accelerating. So that's Alice's experience of time, that's Alice's experience of what Bob is doing. Now, of course, she's not going to see Bob age quickly like that. She's not going to see that. She's just going to see because we haven't talked about how the signals from Bob will reach Alice and all that sort of thing. But that's her picture. That's how she experiences, that's how she would calculate simultaneity for this case. So I hope that's convinced you then that even the true paradox, that the two observers should each see the other one come back younger, is actually resolved if we're careful about who is and is not an inertial observer. Bob's path agrees beautifully with what we assume about relativity. Alice's path does most of the time, but there's one moment in the middle where it is not an inertial path, and therefore we can't we can't believe that it does what we thought it did. They are not equivalent because of that moment of acceleration far away. That's the twin paradox. I think the diagrams for me help a lot in understanding it, and I hope they helped you too.